This is a video for AQA Mechanics, Center of Mass and Moments, section 1.6, which looks at the center of mass of a solid of revolution. This diagram illustrates the idea then we have here some object which is being given by a function y is a function of x, and that's been rotated about the x-axis to produce a solid of revolution. The center of mass of an element would be at the center of the cylinder of that element, so that's going to be on the x-axis. So you can see that the center of mass of any solid of revolution is going to lie on the axis of revolution, and therefore we need only consider the x value of that center of mass. Now for that element, the position of the center of mass will be at x. The mass of the element will be given by its volume multiplied by k. So we need to work out k multiplied by the volume of that cylinder, which will be the area pi y squared delta x. And therefore the moment of that element about 0, the origin, will be equal to the mass k multiplied by pi y squared delta x multiplied by its distance from the origin, which is x. So therefore the total moment of the object we can calculate by summing all of those possible elements, which as delta x approaches 0 becomes an integral. So the total moment about the origin will be equal to an integral. That will be in general from a to b, depending on the limits that we're looking at the object, and we have then k times pi y squared x dx. The total mass, of course, we've seen that the volume is calculated by an integral of pi y squared dx, so the total mass will be k multiplied by that volume. We can therefore work out the center of mass by saying that m total mass multiplied by x bar must be equal to the total moment. And therefore x bar will be equal to these two integrals divided by each other, and of course k will then cancel out from those. So in summary then, we have that the center of mass can be found by an integral from a to b of pi x y squared dx. Remember, this comes from the moments, and then we're dividing that by the integral of pi y squared dx, which is an integral for the mass. So let's look at that now in a particular example. Here we've now given the function of y as being equal to the square root of 9 minus x, and we're looking at this object for x greater than or equal to 0. So our integral is going to run from x equal to 0 up to x is equal to 9, and we need to calculate the total moment of each of these disks and then divide by the total mass. We've established the idea that the mass will be equal to k pi y squared dx, and the moment the integral of k pi y squared x dx. And we can therefore say that mx bar is equal to the total moment, and therefore we get that x bar is equal to the total moment, which will be equal to the integral from 0 to 9 of k pi y squared x dx divided by the total mass, the integral from 0 to 9 of k pi y squared dx. But we know that y is equal to root 9 minus x, and therefore y squared must be equal to 9 minus x. So we can substitute into those that x bar will therefore be given by the integral from 0 to 9. K's are going to cancel out, so you end up with pi times y squared x. That will be 9 minus x multiplied by x dx. And on the bottom line we have pi also, and then the integral from 0 to 9, this time of 9 minus x dx, which is y squared. See also that the pi will cancel out from this calculation if you wish. So we end up with having to evaluate the integral of 9 minus x multiplied by x, or 9x minus x squared, and the integral of 9 minus x dx. Let's just run through that again so we're clear about what's happened. We've taken the fact that the mass multiplied by x bar is equal to the total moment, and therefore we can say that x bar is equal to this these integrals divided by each other. This is on the top line the moment, and on the bottom line the mass. And then substituting y squared is 9 minus x, we end up with these integrals to evaluate. As I say, we could then divide through by k pi, and so we need to evaluate 9x minus x squared dx and the integral of 9 minus x dx. Those are relatively straightforward integrals to evaluate. 9x obviously becomes 9 over 2x squared, and then x squared becomes 1/3 of x cubed, so minus 1/3 of x cubed. That's evaluated between 0 and 9, and then we're dividing that by the integral of 9 minus x, so that's then 9x and minus x squared over 2 evaluated between 0 and 9. Substituting the value 9 into the top line gives 9 over 2 multiplied by 9 squared, so that's 1/2 of 9 cubed, and then we've got minus 1/3 of 9 cubed. Obviously putting 0 in gives 0. Then dividing that by the bottom line, which is going to be 9 multiplied by 9, so 9 squared, and then minus 1/2 of 9 squared. So in total on the top line we've got 1/2 minus 1/3, which is equal to 1/6 of 9 cubed, and on the bottom line we've got 1 minus 1/2, or 1/2 of 9 squared. So therefore it becomes 1/6 divided by 1/2, which is 1/3, and 9 cubed divided by 9 squared is 9, giving us an answer of 3. So therefore, finally we can say that the centre of mass is at a position 3, 0. Remember that the 0 comes from the fact that the centre of mass of the volume of revolution must lie on the x-axis. So in summary, we have that the centre of mass of the uniform volume of revolution we can find by integration. It must lie on the x-axis by symmetry, and we can calculate the position of the x value, x bar, then by considering the moments. So this is the sum of the moments divided by the sum of the masses of each of the elements, so this is the mass. Obviously the k has cancelled out from that particular expression. So you could start with this as being the position of x bar, and of course also notice that pi is bound to cancel out from those expressions. And that concludes this video on centres of mass of revolution, and indeed concludes the series of videos center of mass and moments, section 1.